Okay, we're going to combine our ideas of rigid body energy and work and discuss the principle of work and energy for rigid bodies. Well, principle of work and energy is just the same as it was for a particle. We have kinetic energy plus the sum of our work from 1 to 2 equals our kinetic energy out. And that is our relationship. So let's look at a quick example. Here in this example from our text we have a bar with a spring and a slot, and as we apply a moment, 50 Newton meter, and a force at the end of 80 newtons, this rotates to the right. Now let's look at this when theta equals 90 degrees. And let's determine the total work done at that time. So let's draw ourselves a free body diagram here. We have a force of 80 newtons coming in from this direction. We have an applied moment of 50 Newton meters. The spring causes a force in this direction. We have a beam weight here. Our beam weight has a mass of 10 kilograms. So if we multiply by 9.81, we'll have our weight. And then just for reference, this thing is theta is in this direction. Turn off that ink to shape. And then we have reactions. Let's go with an AX this way and an AY this way. I'll draw these in red because AX and AY don't contribute to any work done since that's a pin joint. Okay, let's begin with the weight. So the work of the weight is, well, we have the weight, which is 98.1, and the distance that our center of mass moves, if the half of this rod length is 1.5, when we go to 90 degrees, it's going to be, if we start at 0 and we go to 90, then we have moved a vertical distance of 1.5, and that is our 147.2 joules. Next, let's look at our moment. So our integral of our moment is 50. It's constant. We go from 0 to 90 degrees, or pi over 2. So we're essentially going to have 50 times pi over 2 as our work, and that equals 78.5 joules. So for spring force, all right, in this problem the spring is unstretched at 0.5, so when it's at 0 degrees the spring is stretched by 0.25, so we're going to have that in addition to our additional length of our spring. And since this slot is able to slide, it will slide directly over this pin when we're at 90 degrees, so it'll just be the length that this string pulls down there. So our spring force is then, or rather our work done by the spring is again minus 30 is the K value of the spring, and then 2.25 squared minus 0.25. And let's get rid of these internal parentheses. And that results in a negative uh, 75 joules. Finally, our force P is applied. We're going to assume it's always perpendicular to the bar here as we rotate through theta, so it's going to follow the arc length. So 80 times pi over 2 times 3 meters. That's going to end up being 377 joules. All right, so our total then for the system, I guess I only need one line here. Our total for the system is 528 when I add all these up. And that is our total work. Next, let's work through this fundamental problem. We have a wheel being pushed by a force P at 30 degrees to the center. The diameter or the radius of the wheel is 0.5, and it's a 50 kilogram wheel, and we got a 50 Newton force. We'll use a radius of gyration of 0.3 here. We want to determine the angular velocity after 10 rotations. Okay, so let's draw a free body diagram with all our loads on it so we can easily determine our work. So we've got 50 times 9.81 as a weight. Then we have a normal force here. I'm also going to draw that in red. Drawing these in red because these are not going to apply in our analysis. And then I have a force of friction which opposes the motion of the wheel here, and a 50 Newton force. Okay, we have no slip occurring, and let's use our principle of work energy. We're going to have an initial kinetic energy, our summation of work from 1 to 2 equals our final kinetic energy. Okay, our initial kinetic energy is 0 since we start from rest, which means we just have to figure out what the work is here. Our final kinetic energy is, well, we'll put that in a second. Let's figure out the work. So we don't have any work performed by the weight since there is no motion in the y direction, and there is no work performed by the normal either. The frictional force could potentially be a work situation, but since we don't have slip occurring and we have an instantaneous velocity at the point of application of that frictional force, then we have no work caused by the frictional force. So everything is out of this except for the force P. And now we only have the horizontal component of this P that does any work. The vertical component, there is no motion in the vertical direction. So it's our horizontal P component. And so we can set up an integral from 0 to x. Now P cosine of 30 is going to be a constant. We'll end up pulling that out. But this x is the distance rolled. So I'll just put distance rolled. This now equals 1/2 mass times the velocity of g. We'll call this g squared plus 1/2 ig omega squared. So we can pull that constant out, and our bounds of integration are 0 to, now x is going to go actually to a circumference that of 1 revolution is going to be 2 pi r, or 2 times pi 0.4, and then we're going to do that 10 times, so times 10, and then we equal 0.5 times 50 times omega times RR of 0.4 squared plus 0.5 times 50 times 0.3, which is our radius of gyration, squared omega squared. And this omega up here also needs to be squared. So our result then turns out to be 1088 Newton meters equals 6.25 omega squared, or omega equals 13.2 rads per second. So really the key to this analysis is setting up a proper free body diagram and recognizing which forces are associated with work and which are not.